fill in our blanks here. We've got about 2.5 pages of notes today and about 2.5 on Thursday as well. Okay, we left off at this location talking about spring constant, which is good because that's what we talked about last semester as well, spring constant. So when it comes to spring constant, it's a spring we know that has a large spring constant value. It's definitely going to be more difficult to stretch out. We did these math problems last semester. So we've got 3 practice problems. Example problem number 1 is pretty easy cheesy. It says, hey, you've got a load with a force of 45 newtons that's hanging on a spring. The spring is stretched a distance of 0.14. My question is, what is the spring constant value? Or F equals K times D. Again, that's elastic force equals the spring constant times the distance. Or, for this situation, it would be 45 equals my K value that I don't know times 0.14. I'll divide both sides by 0.14, 0.14, and you can see just basic algebra. Your K value is blank newtons per meter. So this is an easy cheesy equation. I don't see any of us, because we did this one already last semester, I don't see any of us having problems with it come quiz or test. But this is example problem 2 and example problem 3. Why did I do that? I don't know. Example problem 2 and example problem 3. Example 2 actually is more like what we would see on quizzes or tests. And the reason why is because it's 2 parts. It says that there's a mass of 0.55 kilograms. It's attached to a vertical spring and it stretches at a distance of 0.02 meters. What is the spring constant? Question mark K value. Okay, what's the K value? So the problem here is that I need force for newtons, I'm looking for K value, and I do have distance. Where's my force number? It's actually not given to me. But because I recall last semester F equals ma, then I can solve for this by multiplying 0.55 times gravity, 9.81, to come out with 5.39 newtons. So we need to recall this information so that way we can do step 2. That's where I think it's a really good problem. Some of us may or may not remember or recall that. Part 2 would be the F equals KD equation, or 5.39 equals K times 0.02. Divide by 0.02, divide by 0.02, my K value in newtons per meter. So not too bad. I think we can do this on our own. I just think some of us needed that recall of the force equation. When you're ready, I'm going to leave practice problem 2, 3 for you to do on your own right there, and I'm going to turn the page. Alrighty. Well, look at this. Do you remember when we took our notes, I don't know, a week ago? Sure enough, we actually wrote in our notes. So for those of you who did that note card, this was the same day we did our notes. We wrote down that all waves have one job: carry energy. All waves have one job. It doesn't matter if you're electromagnetic or if you're a mechanical wave. Your job is to carry energy. And if there is no energy to carry, guess what? not moving. If there is energy, you're going to have waves. And the more energy, the higher and the bigger the waves. The less energy, the smaller the waves. Okay? So let's go ahead and let's look at a few properties of waves. It says here, waves are a motion of a disturbance that actually carries energy. We're going to use that word a lot. We're going to have that stuck in our head. From place to place. All waves have the same job. It doesn't matter what type of wave you are. It is to carry energy. A medium is going to be the material / matter through which a disturbance or wave travels through. Now, the medium could be a solid, liquid, or gas. And believe it or not, the type of medium will determine that velocity or that speed of the wave. For an example, oceans or the ocean, it travels through water. If it's sound travels through air, that's the medium. What about light? Light wave, like over here, visible light, it's an electromagnetic wave. It depends where they are. Because right here in the classroom, it's traveling through the air, but if it's a star, its light is traveling through a vacuum in space, no medium at all, okay? So it depends where they are. Where are they? Wave types. Now, a wave can be a pulse, which is what we call a single individual wave. One wave. A pulse is one wave. That's it. Wave. Done. That's it. No more. If it's a periodic wave, we also call that a wave train, where it comes from some type of periodic motion. Wave, 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 wave. It keeps coming. It has more energy for it to travel. Remember, a transverse wave looks like an ocean, up, down, up, down, up, down. But a longitudinal wave looks like a spring or a slinky. Okay? When you're ready, turn that page. Okay? A pulse is a single wave. A periodic wave is what we call a wave train that has a lot of energy to keep giving it. So that way we have more waves. Okay? The next portion here, it says that we've got what we call a transverse wave, which looks like this, or we have longitudinal waves that looks like this. Now, they both have different parts. It says here that a wave whose particles vibrate perpendicular to the direction of the wave, for an example, like a water wave or ocean wave. What I mean is, if this is the equilibrium and all of that is the direction of the energy that's traveling, energy is traveling in this direction, you can see it. This is the equilibrium line when there is no wave. But when the medium or matter vibrates perpendicular this is what we mean. It moves up, it moves down, it moves up, it moves down. And when it moves up and down, it actually forms a right angle. That's what we mean perpendicular. So when the material or matter or medium vibrates perpendicular to the direction of the energy, you can see it right there, they form right angles. Now, a longitudinal wave down here, it doesn't do that. They don't look the same. Now, hopefully we recall the top of the wave is called the crest. The bottom of the wave is called a trough. From crest to crest, we call that a wave length. Or trough to trough, we call it a wave length. And how high up or how far down the wave travels in comparison to the equilibrium, we call that amplitude. Amplitude. All righty. Here's a little bit of review from when we did this wave worksheet. When we did this wave worksheet, we already talked a little bit about the parts of a transverse wave. The equilibrium position is when no wave is produced. It's at rest. It's at rest. The crest is going to be the highest point. The trough is the lowest point in comparison to the equilibrium. In comparison to the equilibrium. Remember, equilibrium is when it's at rest. A wavelength is going to be the disturbance between two similar points. And we're meaning crest to crest or trough to trough, middle to middle, whatever it is, however you want to label it, but two similar points. The amplitude will be the height or distance of the wave from equilibrium. Meaning, the more energy it has, the higher it will travel. That perpendicular vibration will be higher up in comparison to the equilibrium. Okay? So, being able to label a transverse wave, a longitudinal wave are some pretty easy, cheesy things to do on the quiz. Right? Being able to find the spring constant, we should be able to do that on the quiz. Parts of a longitudinal wave. Now, a longitudinal wave is like a spring or a slinky, right? It's a spring or a slinky. So a longitudinal wave is a spring or a slinky. And you can see that if I push it this way, I give it energy. Whichever direction I give it energy is the direction it's traveling. Do you see that little compressed part that travels all the way through it? That's this part right here, the compressed part. When it travels through it, we call that the compression. Where it's spread out, we call that rarefaction. refraction. The compression correlates or corresponds to the crest of the wave. The refraction is the stretched out part, and that corresponds to the trough, that bottom low point. And the refraction compression combined is a wave length, or compression to compression, or refraction to refraction is a wavelength. Okay? So you can label it just like how you labeled it over here, crest to crest, trough to trough. You can do that over here. You can say compression to compression or refraction to refraction. Okay? Now, this one though, its wave vibrates parallel to the direction. What do I mean here? If this is my energy traveling through my wave, and let's call that energy, then the vibrations are going to occur. This one's going to hit that one in front, and it's going to hit that one in front, and that one in front, and that one in front, and that one in front. And you can see, in comparison to the energy, that vibration is parallel to the comparison of that energy. So that's where we get perpendicular and the parallel from. Okay, hopefully you can visually see that. All right, those are parallel, those are perpendicular. All righty, we've got this part, and then I think another page and a half or so, page and a little bit more. That's it. All righty, so let's keep going here. We've got a couple of, and look, I have my yellow highlighter. What do I like to do? I like to highlight the part of the notes for you to fill in, but I also like to highlight the section that is a memorized equation. All right? The great thing here is that these equations are the same ones that we talked about when we talked about circular motion on the first semester. So it's not a new one, it's just an old one that's coming back. Capital T equals 1 over lowercase f. Lowercase f equals 1 over capital T. Hopefully we remember. Frequency is in hertz. Capital T is period, which is in seconds. That should be pretty easy cheesy. Now this equation, the velocity, which is on the formula chart, which is frequency times lambda. Velocity, which we prefer it to be meters per second, but it could be centimeters per second. Frequency is in hertz. Lambda is wavelength, which is in meters. Again, if your lambda is in centimeters, then your velocity would be centimeters per second. Okay? Now I want to go back to that one over there. Period and frequency. So when it comes to period and frequency, unfortunately, you have to have an F or a T so that way you can solve each one of these. They don't give it to you. Do you remember this equation we talked about? Total waves, over total time equals frequency. All righty. So the waves over the time is also another way to calculate frequency. So here, they would like for us to calculate period, frequency, and the velocity. The problem is they don't give us frequency or period. And since we don't have that information, it's easiest to use this equation. The amount of waves, which is 35, pass a given point in a total of 22 seconds, is going to equal 1.58 hertz. And that's the easiest way to calculate frequency. And then we can come over here and calculate period by 1 over f, or 1 over 1.58, which comes out to 0.628 seconds. Again, this is something we did last semester. Please expect for this to be on the quiz this Friday. And our equation over here for the velocity is frequency times lambda, or 1.58 times it by 3 meters equals blank meters per second. Okay? So pretty easy cheesy, or hopefully it's going to come back to you soon. When you're ready, we've got another page. I know, I apologize. Today's kind of a lengthy note day. Thursday's going to be the same way. Now, I'm going to leave these practice problems. We can always come back. I want to do this practice problem because I don't like this one. Let's look at this one over here. Example problem number 6. My problem over here is that it says centimeters, but there's some darn liars. Look at that paper ruler. It's in millimeters. And they want us to calculate this or to measure this in centimeters. So what I'm going to do is I'm going to just convert it. It says here, this is a wave train. It took 1 second for this wave train to occur. First question, how many waves are in this wave train? 1, 2, 3, 4 waves. What is the wave length? Which means how far is one wave? From here to here, using this paper ruler, it's 3, but it's in millimeters. King Henry drinks utterly delicious chocolate milk. Milli to centi, I've got to move the decimal place over one time, 0.3. Amplitude. Amplitude is how far from the equilibrium up it's going to go. So from here, 1 millimeter. Convert it, 0.1 centimeters. Oh, whoa. Frequency. Calculate it. 4 divided by 1 equals 4. 4 hertz. Speed. Velocity equals frequency times lambda, or 4 times point, right here, 3 equals your velocity, centimeters per second. 1.2 is the correct answer. So I just wanted to go over that one first before, I just didn't like how that was labeled centimeters. That was tricky. Now let's get to this part, because this part is the part where we actually are going to go ahead and take a small little pivot turn from what we call traditional physics to a little bit of quantum physics, okay? So here's the thing. I've got this little cup right here, and it's got markers. Got this cup with more markers. And my thing is, I want my where this first cup is. Well, if I do that, dang it, I want them both to be right here. Can I make the second cup be exactly where the first cup is? Is there any way that they both can just merge? They can't. Because two types of matter or two matters cannot, do you remember this from a long time ago? Occupy the same space at the same time. Right? Do you remember that? Like old school science, probably middle school. Two matters cannot occupy the same space at the same time. Here's where we're going to a little bit of non-traditional physics. When it comes to waves, they can. Whoa, whoa. That's where we start to get to a little bit of this quantum stuff. How can two waves occupy the same space at the same time? That's what I thought would have been a good question. But that one's really hard. How can two waves occupy the same space at the same time? Because what is a wave? What is a wave? Nope. What is a wave? A wave is a disturbance of blank that's traveling. What does a wave carry? A wave is energy. Now let's go back to old school. Is energy matter? No, energy is not matter. It doesn't have mass and it doesn't have volume to occupy space. And because energy is not matter, energy or two waves, which is carrying energy, can occupy the same space at the same exact time. Now, there's a few quirks that have to happen, but this is where we're going to start hitting like a little bit of Einstein and a little bit of this and a little bit of that, and we're going to get into lights and a little bit of quantum, okay? Because waves can occupy the same space at the same time. We call this wave interactions. They can interact, and when they interact to occupy the same space at the same time is when two or more waves come together. And they can occupy the same space at the same time. And they do not bounce back. Didn't those cups, when I had one cup there and I pushed the other one, didn't bounce the other cup out of the way? Like it moved them. Like, no, you can't sit here. I'm going to sit here. No, waves can. Because why? Waves are energy that's moving. Okay. So now here's a couple of things we have learned. The problem, though, is that, but Miss Munson, wait a minute. If you're telling me that wave is carrying energy, but isn't it going through matter? So the matter cannot occupy the space at the same time, but the energy can, okay? And because the matter cannot, then the matter is going to do something special. They form what we call constructive interference or destructive interference. The constructive interference is whenever that wave is traveling, and if this is the energy or the equilibrium, and they are on the same side of the equilibrium, then what you do is you add those waves together. You're going to add the matter together because matter cannot occupy the same space at the same time, but a wave can. So if this wave is 2 meters and this wave is 1 meter, and they are about to slam into each other, they're not going to bounce off of each other. They're going to occupy This was before, and this is after. They're going to occupy the same exact space, but instead, they are going to add and combine it to a 3 meters in height. Why? Because the matter cannot take up the same space at the same time. Duh, we know that. But the energy can. Ooh. And so now the matter gets bigger. We call it constructive interference. Whenever the wave is traveling and the wave amplitudes are on opposite sides of the equilibrium, what we do is we subtract the waves. So if this wave is about to collide with this wave before, and this is the after, if this one is 2 meters and this wave is 1 meter, on opposite sides of the equilibrium, 2 take away 1 is 1 meter. And because the 2 meter was at the top of the equilibrium, it's going to win whenever they collide. And it's going to be at the top. Easy cheesy, adding and subtracting. I got that, Miss Munson. I know you do. I know you do. Turn the page. I promise we're almost done. I know. Alrighty. Constructive interference and destructive interference. Now, just a little bit more of vocab in talking about waves when they interact. We call a standing wave a wave pattern that occurs when 2 waves of the same frequency, the same wavelength, and amplitude travel in opposite direction. And what happens when they interfere with each other and they so happen to be trapped? Oh my gosh, Miss Munson, that's a lot of ands. I hear you. In that situation, they go ahead and collide with each other. And when they collide, they form a standing wave. Let me give you an example of a standing wave. The wave is trapped here and here. And it cannot pass this location. And it can vibrate. And when it vibrates like this, it's going to interact and interfere. And when they interact and interfere, they start to make all these other little vibration and these little waves. Have you seen anything like this maybe on a musical instrument? We call that a guitar string. How about that? The guitar string is trapped here, and you pluck the guitar string, and you pluck it again, and every single time. Now it's going to form what we call nodes and antinodes. The node portion is going to be when it undergoes disturbance, which is destructive interference. For an example, right here, do you see that? Destructive. At that moment, those 2 waves collided and they destruct or destroyed each other. What if one wave is exactly the same size as the other wave? 2 take away 2 equals 0. They completely destroy each other at that moment. So a node is whenever it's going to cause a destructive interference. An antinode is going to be halfway between two nodes. And we'll have a large amplitude because of constructive interference, which is going to be right here, right here, right here. Easy cheesy, we got that.